Thank you very much for the kind introduction. So as Luke said, I'm Gabi. I work with Hidoda mostly, which was here yesterday, as I understand. And I thought that I'll present at this talk my interest around proposition extraction, a topic that I've been thinking about during my PhD on the different aspects of it. So formulation through crowdsourcing all the way to prediction. So let's start with an introduction or the what, how, and why of proposition extraction. So propositions are statements for which a truth value can be assigned. Statements like Bob loves Alice or Bob gave a note to Alice. So for each of these statements, you can say that it's either true or false. Bob can either love or doesn't love Alice, and similarly for giving a note to Alice. And typically, propositions are thought of as a single predicate operating over an arbitrary number of arguments. So you can, in the first example, you have 2 arguments, and in the second one you have 3, and it can go on to an arbitrary number of such arguments. And the interesting thing about propositions, I think, is that they're the primary unit of information in a sense that you cannot reduce them any shorter and still have some meaningful information conveyed to a human listener. So the task of proposition extraction is to take a somewhat longer sentence, something like Barack Obama, the 44th US president, was born in Hawaii, and decompose that into the different propositions that are embedded in this sentence. So you can say that Barack Obama is the 44th US president, that Barack Obama was born in Hawaii, and that the 44th US president was born in Hawaii. All of these are conveyed to a human listener, and they stand alone on their own. And there have been many representations in NLP trying to capture specifically that, the proposition structure conveyed in sentences. And I'll review just a couple of them, the most prominent ones. So I guess most of you are familiar with SRL or semantic role labeling, where we try to identify predicates in the sentence. So in this case, we have born, and we also ground it to a specific lexicon. Oftentimes, that would be profbank, identifying what is the meaning of born and what kind of argument do you need to expect when you see this specific predicate. So here we would mark that Barack Obama, the 44th US president, that's the who was born, and Hawaii is the location of that born event. So that's in SRL. OpenIE, or open information extraction, takes a more open approach and uses the text itself to represent propositions, much like I described in the previous slide. So you use the text itself to enumerate these propositions without grounding to a specific lexicon. AMR has been very, or abstract meaning representation has been very popular in recent years, and it takes kind of the SRL approach, but tries to induce a graph structure over the sentence. So you can have the born predicate, and Barack Obama in Hawaii, and Barack Obama specifically also participates in another event of presiding over some state. The no-Davidson approach is a more classical approach, taking more of a functional methodology where every predicate is a function. And finally, MRS, I think, is somewhat similar, or minimal recursion semantic, it's somewhat similar to AMR. But as opposed to AMR, it grounds to this, it has a mapping to the specific words in the sentence. So you know that Barack Obama is the specific entity, as opposed to here, you have no connection to the specific words in the sentence. And even in AMR, you can have some more abstract concepts coming up that are not available in the sentence. Yes,
sorry
sure.
to interrupt,
Yeah.
if you don't mind going backwards. I know you're trying to get to the meat of the talk, but this is such a wonderful summary, and
Cool.
so I just want to ask a couple of questions. First of all, I was confused by the last thing you said about the connection with the words of the sentence,
Right.
because in the example, looks like
Right,
Barack Obama is right there.
It's right there, but it's a text. It's not the third token in the sentence. You have no direct connection. And actually, there's been, when you look at an AMR, you can even have predicates that are not there in the sentence. They are implicit. It's true that this example doesn't demonstrate that, but this is.
The person who's there.
Yeah.
Just a little bit of extra content.
Right. Yeah, and it's true. I could have added more abstract concept, and that would be fine with AMR. And there's been work trying to take AMRs and align them to the sentence. As opposed to here, at MRS, you ground it to the sentence immediately. You have, I mean, this is the first token in the sentence. It's not some concept of Barack Obama.
Right. I guess the part of what you're saying that I'm not understanding is there's the string Barack in the AMR
Right.
representation. So I see an exact mapping to the sentence. I'm just not understanding.
Yeah. So in this case, it's true. But if you'd have, you can have example where it's not that straightforward.
Okay, so
Yeah.
so we can't see it in the example.
Right.
Is the short answer.
Yeah, yeah, yeah.
You guys were both alluding to aspects of the example, and I just don't see it. The second thing is when you contrast the neo-Davidsonian with an AMR with the other representations. I understand clearly the distinction between SRL and OpenAE. You said in one case it's grounded in certain ways like lock and word-sensitive disambiguation. The other one you said, yeah, it's got a function, it's old, but my question is, what's the difference between these representations?
So here, I think you need, so you mean between SRL, for example, and OpenAE?
Well, what I'm trying to say is you laid out 5 representations, but then when you describe neo-Davidsonian, for example, you refer to incidental aspects of it.
Yeah.
Happens to have a function, there exists there. I'm just asking, what's the difference from the representational point of view?
So if we contrast it to OpenAE, so here you have a specific function, right? So that's one difference. If you contrast it with SRL, you have a structure. If you contrast it to AMR, I guess there's some agent which is predicate global for all predicates, something that AMR wouldn't have. It takes the SRL approach. So these agent and themes and locations are global, are not for a specific predicate. So that's one difference.
Okay, but is there, my last question,
Sure.
I'll let you go. So I understand that there are specific differences
Yeah,
in this, and whether they're...
And there's a lot of commonalities, I agree.
And there's a lot of commonalities. So I guess the question I'm trying to ask is, if I go start a project to represent sentences, I feel like when I choose between OpenAE and SRL, I know which one is going to serve me better. If I need the particular, say, word-sensitive disambiguation, and I need to know what the locations are, it's natural to use SRL. The question I'm trying to ask is, what are the real trade-offs between these representations as opposed to idiosyncratic aspects of them,
Right,
given that they have so much in common?
Right, so I agree, and that's what I'm researching as well. So I'm interested in contrasting these, and there's a lot of commonalities, and I don't think that there's a lot of work trying to say, I mean, people work specifically on this, and they entrench themselves in some specific representation, and not necessarily try to map them according to other aspects. So there must be a lot of overlap between them, as I mentioned. But I'm definitely interested in what would work best. And I think that's an open research question.
There was just an ACL paper
Yeah.
by Miyavan and another report which studied
Yeah.
5 or 6 of these representations and kind of compared them and found commonalities in them.
Yeah, so I think that that's like an active field of research, I think. And also, I was surprised that a lot of works at ACL also targeted MRS, which I thought was, I mean, we were gaining a lot of interest in it, and we weren't sure if it's still alive. And one of the outstanding papers was state-of-the-art parser for MRS. And one group from, so one of Noah's students has made a way to study, to predict some of these in a multitask learning scenario. So I think, and they also studied like the interaction between that, and I think that's an interesting question. Yeah. So why? Why do people want different representations? And I think this maybe will answer some of your questions. So I will show just a few prominent works that have used different representations. So they chose these different representations for different representational aspects that they had. So for summarization, in recent work by Liu et al., I think from CMU, they've taken several sentences, several AMR representations, and have merged them together, and then produced one sentence from the merged representation, which they claimed was a good summary of the set of sentences. So that's using AMR. Using OpenAE, Angeli and Chris Manning from Stanford in 2015 have used an OpenAE system to populate a knowledge base. And over there, what they found useful was this open and very robust nature of OpenAE as a way to extract a lot of information from large amounts of text. And they've achieved state-of-the-art results for knowledge base completion at the time, at least. And for question answering, so Shen and Lapata have shown that if you use the roles from SRL, as I've shown before, something that OpenAE, for example, doesn't have, you can improve question answering. So we can see here like different aspects of the representations helping different semantic tasks. But I think that another complementing trend would be to say I train directly from the sentence to some task. So I don't need any intermediate representation. I just take a bi-LSTM with some attention, for example, and train from the words directly to some task that I want to solve, like machine translation or whatever. I don't need an intermediate representation. The neural network itself would learn some useful representation for the task. And I think that this is a valid and fair approach, but on the other hand, I think that in recent times, very recent works have shown that if you take a neural approach and integrate some proposition structure or some semantic structure into the work, you can get gains by integrating it in a soft manner, some representation of the structure, and I'll survey a few. So last year, ACL, Vered Schwartz from our lab, have used encoding of dependency path to get state-of-the-art results for hyperonymy. And in a very similar work that was done on the same time, Roth and Lapata also encoded dependency path into some neural architecture, and they showed that they can improve semantic role labeling by using it. And very recently, just a week ago, Roy Aoroni and Yoav Goldberg have shown that if you add a syntax to the target side in machine translation, you can get better machine translation, which gives more syntactically correct structures that resemble English more closely just by adding syntax at the target side in an automatic manner. So I think that these works all show that you can use syntax in neural architectures, but I'm very interested to see whether we can have some more semantically oriented structures integrated in this soft manner as features for neural architectures, and that way get some more gains and get better performance in similar tasks. So hopefully now you're on board with wanting to get propositions extracted from text, and I'll present some of the research questions that I had during my PhD. And I think they span the different aspects of proposition extraction. So starting from the foundation, I asked myself what are the desired requirements from proposition extraction? So similarly to Oren, I also want to know what would be best for applications to get out of propositions. What are the specific requirements that would work best for each specific task? Once we have this formulation, I want to get them annotated on a large scale. I'm very much interested in trying to get complicated structures annotated in an intuitive way from the crowd, as opposed to, for example, prop bank, which was annotated by experts, and similarly AMR, which is a very complex structure and a very expensive process to annotate. I'm interested to see whether we can crowdsource complicated structures and get a larger scale by these annotations. And once we get these annotations, I want to see, can we effectively predict proposition structures given these annotations that we had on a larger scale? Right, so the outline of my talk would try to exemplify two research projects that I carried during my PhD, which I think exemplify this cross-section of proposition extraction. So we'll begin with non-restrictive modification, and I think that we had a nice trick there for crowdsourcing that I mentioned before that I'm interested in. And then once we get this annotated, I'll describe the prediction of non-restrictive modification through CRF and some linguistic features. That's the first project. The second project would be supervised information extraction. That's actually a work in progress that I'm still working on. But we have some published work on this where we try to formalize what are the requirements that we want from OpenAI, try to set it up front and say this is what we want from OpenAI. And then we automatically convert QA-SRL. I will go into this in much detail. From QA-SRL to OpenAI. And once we have this fairly large corpus of open information extraction, we want to model it with bi-LSTMs to get state-of-the-art results on that corpus. OK, and after that, I think I'll outline very briefly some of the interesting avenues that I'm interested in exploring. And I think that there's a lot of possible avenues to explore further from leading up from these kind of works. So let's start with the first project of identifying non-restrictive modification. And let's start by looking at argument spans in general. So if we look at the previous sentence, arguments are typically perceived as answering argument role questions. So looking at the sentence, we can answer who was born somewhere or where was someone born. And in most annotations like AMR or prop bank or neo-Davidsonian, this is very much implicit. You don't see these questions even though the arguments themselves answer them. But as opposed to that, recent work by Lu Heng He and Luke and Mike, right? From 2015, I've annotated SRL specifically with these explicit questions and answers from the crowd. So looking at the sentence, we would get these kind of questions and the appropriate answers for them. And we will make use of these annotations in this work. So I would claim that most semantic annotations take the inclusive approach when they annotate argument spans. So if we look at the sentence, and this is a syntax tree, so most annotations would say that this is the entity who was born somewhere, Barack Obama, the 44th US president, and this is where was someone born. And they would take the inclusive approach in a sense that you would annotate complete syntactic constituents as arguments. But I asked, can we go shorter than that? Can we give a sufficient answer that's shorter than Obama, the 44th US president? And I think that we can. We can just say who was born somewhere, Obama, and that's a more concise yet sufficient answer than Obama, the 44th US president. And there's a lot of motivation for doing this reduction, and these are just a few examples. So for sentence simplification, I think it's pretty straightforward. If you can drop certain modification, you can make a long sentence much more simple. For knowledge-based completion, as I mentioned before, if you have smaller arguments like Barack Obama instead of Barack Obama, the 44th US president, it's more likely to reoccur in the text. You're more likely to find more instances of Barack Obama as opposed to the various ways you can modify Barack Obama in different texts. And for text comprehension, our work with Mausam in 2015 have shown that you can get better text comprehension by using OpenAE, which specifically reduces the argument. So one way of shortening arguments is through non-restrictive modification, which is the examples that I've shown before. So our restrictive modification would be an integral part of the meaning of the containing clause. That's a linguistic definition by Huddleston. And a non-restrictive modification would present a separate or additional unit of information, similar to the examples that we've seen before. And I have just mentioned in passing that another type of reduction is removing non-distributive coordination. So you can split certain longer arguments. If you have Barack Obama and Bill Clinton were born in America, you can separate that into two separate propositions. Barack Obama was born in America and Bill Clinton was born in America.
Is it easy to tell between the two?
What?
Is it easy to distinguish?
Yeah, so that's what we're trying to do in this work. In this work, we'll try to identify between these two. I think that these would often occur with coordination, so that's a good sign. And these would happen with NP modifiers. So here you want to identify NP modifiers which are not integral to the meaning of the entity. Yeah, so this complicated slide, we don't have to read all of this, just demonstrate that the problem of identifying restrictive versus non-restrictive modification is a very semantic task. So based on syntax alone, you cannot identify whether it's restrictive or non-restrictive. So this column has restrictive example, and this one has non-restrictive, and the rows are different syntactic constructions. So for example, for relative clause, if we look at the sentence, she took the necklace that her mother gave her, so this modifier here in orange is a restrictive modifier, right? You need that modifier in order to identify the specific necklace that she took, as opposed to the speaker thanked President Obama who just came back from Russia, which you can drop. So both of these are relative clauses. And we can look similarly at the different syntactic construction, each of which has a restrictive and a non-restrictive version. So syntax alone cannot give enough clues. So the goals here would be to create yeah.
On that previous slide, why is the non-restrictive example you have for propositional modifiers different from the relative clause at the top? So Franz Ferdinand from Austria, surely I need to know.
I think, yeah, so I think if you look at the syntactic structure of the first one, this would be identified as a relative clause modifying this entity, and this would just be a preposition. It would get different syntactic analysis.
I'm sorry to
Sure.
show that I was looking at attention also everywhere. But let's take just the first example then. Can you work that a little bit through, like,
Sure.
why do you call the red thing restrictive and the blue thing non-restrictive? Because they seem to me like the same. Like
All right.
tell additional information about the specific
Right.
thing.
Right, but here, if I would drop the blue one, would you still identify the specific thing that we're talking about? It's not the specific Obama who thanked, right? It's not. I'm not trying to identify an entity.
Okay.
As opposed to the other one, which I'm
Right.
trying to, right? Here, you wouldn't know which specific necklace, okay? Yeah, so good questions. Is that fine, or?
But if you drop from Austria, surely it can be any transfer.
I agree that it's a gray line, yeah, but for a listener, I mean, aware to them some specific historic, it's a specific transfer then. But I agree that it's a gray line.
Okay.
So the goals here would be to create a large corpus annotated with non-restrictive modification. And as you've seen, like with these questions, we want it to be crowdsourceable with good agreement levels, and it's fairly hard, as you've seen. And once we get this large corpus annotated, I'm interested in automatically predicting whether a modifier is restrictive or non-restrictive. So let's look a little bit at previous work. So there's been 2 works trying to annotate specifically this concept of non-restrictiveness. The first work is fairly simple. That's by Hannibal et al. They took the CCG bank and they tried to add non-restrictive annotations to it. And the way they did this was to look just at the comma separating the clause. So there's a syntactic rule in English where if you want to introduce a non-restrictive modifier, you would put it in commas. So Barack Obama, comma, the US president, comma, something. But they did this specifically to show some extrinsic gains, and they didn't necessarily test the intrinsic correctness of this approach. They didn't test whether these annotations captured all or some, or they didn't do any precision or recall metric to test that. And another recent work, which was more in the line of what we're doing, is by Dronescu et al. In 2014. They actually annotated the concept using human annotators, which had to do 2 tasks at once. They had to mark spans as modifiers and then decide whether the span is restrictive or non-restrictive. And the fact that they had to do these kind of annotations, I think, led to pretty bad agreement, as they themselves report. So they reported 2 agreement levels, one on the span, just agreeing on the span of the argument, and that was pretty low, but then restrictiveness was pretty good. But overall, this non-consistent annotation led to some pretty bad performing models, around 47 F1. And they use some CRF with chunking features to identify whether a modifier is restrictive or not, trained on their non-consistent corpus. All right, so now we're ready to get to our approach. So I think the trick here would be to present question and answers to non-trained annotators and gain some non-restrictive annotation from that. So here we have the syntax tree of the 2 sentences that we discussed before. She took the necklace that her mother gave her, and the speaker thanked President Obama, who just came back from Russia. And the way we do this, we start from a predicate, from a verbal predicate, and we move to an NP modifier. So from the predicate, we move to this modifier. We can identify that in a straightforward way from the syntactic tree, from gold syntactic parsers. We then phrase an argument role question answered by the NP. So we can ask, what did someone take, right? The necklace which her mother gave her. This is answered by the entire argument. And similarly, we can ask who was thanked by someone, President Obama, who just came back from Russia. We then drop the specific modifier that we want to annotate. Now we want to annotate which her mother gave her. We want to annotate it as either restrictive or non-restrictive. So we drop the modifier and show the full answer and the short answers to Turkers and ask whether these specify the same answer as this one. Similarly, the same way that I presented the task to Christian just a minute ago. And very similarly to how you responded, right? It turns out the Turkers are pretty good at identifying that you need this modifier in order to still identify the same answer, and you don't need this one to identify the specific entities that you're dealing with. Yes?
This is so incredibly contextual.
Right, but they look at the sentence. They have everything. They have the sentence, they have the question, they have the long answer.
If I were to talk to my wife and I said, she took the necklace which her mother gave her in something, and I said she took the gold necklace which her mother gave her in something completely different in this framework, because me and my wife know that the gold necklace is
I agree.
that specific thing already.
I agree that there's a lot of subtleties.
But the talker wouldn't know that.
Right, but you don't deal. But this is a lot of like private talks, I think. And when you look at the news domain, you do have to address a larger audience. So there's a lot of common sense going on. So maybe the agreement would be better, as we'll see. But I agree. There's a lot of subtleties, but you have gains to get from doing this, from reducing the arguments, as I've seen before.
Which is great. I mean,
Okay, cool. No, but I agree that there's a lot of subtleties going. Yeah.
So what exactly is the task? They have two question-answer pairs, and they have to say which one is.
No, so they have one. They have the sentence.
Right.
They have a question-answer pair.
Right.
The longest one, and then they have a short version of the same answer, and I ask whether it's the same. It provides the same information as the first one. Whether it still provides the same answer to this question. So in the context of a question, it's easier to frame the task.
I see. Are you going to go into more detail on what exactly, like, what the task looked like, or is
This is the task. So yeah.
I wonder though, given the sentence, there's a set of entities that are referred to, right?
Okay. Yep.
And the necklace actually refers to a single entity, the only necklace that's ever been mentioned. So I don't understand how this gives you different answers between the two. Right?
No, but you would see the longer answer, right? So it's similar to what I presented to Christian when he asked, how is this restrictive? And I asked, does this provide another, does this identify a specific necklace in a possible world? Did the speaker use this to provide more information on a specific entity?
Yeah. So what you just said was more information than what you said the task had.
Right. So we
You
had
said we have a
no.
specific
You know,
world.
there's some specific phrasing that we settled on. I mean, there was a lot of iterations. So yeah.
I'm just curious about
Okay.
that.
So I can elaborate on that.
to me, it looks like the tasks distinguish between common knowledge and contextual knowledge.
Yeah.
In a specific piece of text or in whatever necklace means something, in general, given all human knowledge that's commonly shared between reasonable humans, necklace, we don't know what necklace we're talking about.
Right. So that's what we're trying to aim. But yeah, if you want to look at this, if you want to take a look at the specific guidelines, I can share that with you. Okay, so we took the Connell 2009 dependency corpus, and we took specifically that corpus because we had these questions already from QA-SRL. So we had these questions and those answers paired with some syntactic structure. So we had all of this framework going on for us. And each NP was annotated by 5 annotators, precisely to test agreement, and 5 cents each. I don't know if it matters for you. And the consolidation was made through majority vote. And a nice property that we have here is that we can analyze the corpus because we have gold syntactic parsers. We can see which kind of modifiers are easier for people to annotate, on which they tend to agree more. So we can have this analysis split based on gold syntax. And we can look at several conclusions here. So one, prepositions. So I think the question that someone asked here, that's specifically a harder one. So we can get lower agreement level specifically on prepositions. So the from Austria part, that was indeed confusing to some people. And similarly for appositions. But that may be a quirk of the annotations because the appositions are supposed to be non-restrictive by nature. So there's something here. But overall, I think that a nice property of the corpus overall is that we have a pretty fairly balanced between the two classes. So if we look at the entire corpus, 51% is non-restrictive, and the other 49, 48% something, yeah.
Really got 100% agreement on relative problem?
It's just that it's very small, I think.
Right, but still, I mean, you had 5 annotators.
Yeah, so apparently the instances themselves were very easy, yeah.
Okay. Did you have to somehow sample it?
Oh, and also most of it was non-restrictive, so I guess the examples were very easy. It's a very small test set for that specification. Yeah, yeah.
Did you have to do anything special to get that balance, and then just fall out?
We didn't do anything specific to the corpus. Yeah, well, we did do a lot of iterations to get, the right annotation going, but after that, yeah. All right, so now that we've got this corpus, we wanted to train a model to predict non-restrictive modifiers from text. And we used CRF features because we thought that for once the corpus is fairly small for neural architectures. And also previous work have used CRF as well, so we wanted to compare more clearly with them, the work that I mentioned at the beginning. So, and the features that we used were try to look at the literature and see what kind of signals can give us a clue that we're looking at non-restrictive modification. So one is the dependency relation, as you noted. There's some signal there, so non-restrictive. So relative clauses tend to be non-restrictive, for example. NER, I think a lot of the examples here were using Barack Obama as a named entity, and the modification of a named entity tends to be non-restrictive. Word embeddings, so for once they're cool, and for another purpose, if you have contextually similar words, even though you didn't see them in the test set, so maybe this some contextual similarity also predicts similar restrictiveness value. And finally, we had some linguistic motivated features. So I don't know if you know this, but the word preceding the modifier also is supposed to indicate whether it's restrictive or not. So you're supposed to use which for non-restrictive, I think, and that for restrictive, or the other way around. One of the two. But it's supposed to be a signal, right? And I don't know if, I certainly don't use it that way. And also British
English differs from American
Yeah.
English.
So we had that. And also maybe formal language would be more aware of this. And we also added commas, which other previous work have identified as signal. So let's look at the results. And let's break this down. So here we have precision, recall, and F1 for the different systems. And similar to what we had for the agreement, we can split it according to the syntactic structure, right? So we can see how well we do on each of the syntactic rules. And we have the different systems. So Honeyball, just to remind you, that's commas, just based on commas, if you have commas. This is CRF chunking features, which we retrained on our corpus, right? So they trained on their corpus, but we re-implemented and trained on our corpus. And this is the features that I just mentioned. So for once, we can see that prepositions and adjectives are harder to predict. So I think this correlates with what we've seen for annotation. It's harder for humans to annotate. It's harder for our models to get a consistent signal from that. Yes?
This is precision of restrictiveness or non-restrictiveness?
Restrictiveness, I think. That's a good question. Yeah, so we framed it as restrictiveness, yeah, the precision of that. If we look at commas, commas are good for precision. So we can see that it does pretty well in precision. So if you have commas separating a modifier, it tends to be indeed non-restrictive. But on the other hand, recall is very small. So you do miss a lot of the true cases you don't get to because you classify them as non-restrictive, which leads to a fairly bad performance on our corpus. And Dornesco et al., they actually perform much better on our data set. So to remind you, I think they did around 30-something F1. And when we retrain them on our corpus, they get better performance. And I think this indicates that our corpus is more consistent with the annotations, and their features are actually better than what they are shown on their corpus. And finally, our system improves recall. So if you look at the performance difference here, it's not really different, but we get around 10% in recall. So our added features do capture a lot of the positive instances. So to conclude just this part, we created a large corpus for non-restrictive modification, directly augmenting dependency trees. So the way this corpus is published, for each NP modifier, you have another tab indicating whether this is restrictive or non-restrictive. And that's the way we published it. And we also published an automatic classifier, which improves our state-of-the-art results for this corpus.
Are the dependency trees machine generated?
No, gold, because we took the gold kernel parses. So we just take the gold corpus and augment it. So it's a kernel format, right? So you have another gold column indicating whether a specific modifier is restrictive or non-restrictive. Yeah, so any questions about this? I guess we can, or we can keep it to the end and you ask as we go. That's good. Right, so that was the first project. The second project is supervised open information extraction. And we start with trying to formalize what we want out of proposition extraction. So this was presented, I didn't say the previous work was presented at ACL 2016, and this was presented in EMNLP last year. So the problem that we're dealing with here on our way to supervised open information extraction is that we don't have a large corpus annotated with open information extraction. And I will describe open information extraction in a second. The approach we are going to take would be to identify common extraction principles in recent work on open information extraction. We will then extract a large OpenIE corpus or convert a large OpenIE corpus from QA-SRL that I mentioned before in my previous project. And we will then train a transducer bi-LSTM, producing a label for each word and producing BIO tags for OpenIE. So let's start with looking at OpenIE. Maybe we'll do this briefly because we've seen that before. So we get these tuples in open format, and they've been useful for a lot of applications, as we've seen before. So we want good OpenIE. And actually, a lot of people wanted, and we can see that there's been a lot of work trying to produce OpenIE parsers. These two are from last TMNLP, and this is just a small sample. There have been more than that. But as opposed to this vast interest in OpenIE, there hasn't been a good definition of what is OpenIE in terms of common guidelines. And subsequently, there's no large corpus for OpenIE evaluation. So the way most OpenIE parsers take to evaluate is a post hoc evaluation. They run their system on some text, they look at the output, and then judge, usually by themselves, whether some extraction is correct or incorrect. And this leads to precision-oriented metrics. You can't know what you missed. You can't know what extractions are not there if you mark your own extractions. The figures, the numbers themselves are not comparable between systems because you have different people annotating different extractions every time. And the experiments are harder to overall reproduce. And this is just a sample of previous work. So we have different number of sentences, different genres, different metrics, different number of annotators, and different agreement metrics. So overall, it's very hard to say that CLOSI is the best OpenIE system, for example, or that OLI is the best one. So this is the problem that we're trying to deal with. The first part of the solution is, as I said, to identify common extraction principles. So first, I think underlying in all OpenIE work is that you should have an open lexicon. You shouldn't ground it to some specific meaning representation. Second of which, the extractions should stand by themselves and be correct with respect to the sentence. So if you look at the sentence, Cruz refused to endorse Trump. This was true for EMNLP. Yeah, I should update this. So it wasn't true back then that Cruz endorsed Trump, but now it's true. So you need to take the complete context, right? You need to take the complete context to represent what was said in this sentence, which was true back then. And second of all, very related to the previous work, thirdly, the third point, you want to have shorter argument spans. So if you can get Hillary promised better education, social plans, and healthcare coverage, I think most OpenIE systems, and by reading their papers and by looking at what they want to split this into several standalone propositions, each of which can be used in a downstream system, as opposed to just extracting a single proposition saying Hillary promised all of this. So this is a distributive conjunction. So following these principles, we tried to compare different representations and see whether some representation is close enough to OpenIE that we can maybe bridge the gap, following your question about the differences between representations. So there is some connection between OpenIE and traditional SRL across these different requirements that we want. But it lacks in open lexicon. If you look at traditional SRL, you have some grounding. And the arguments by themselves are not reduced. As I've shown in previous slides, you tend to annotate a complete syntactic constituent. So by their nature, they're not minimal. But what we found in QA-SRL, first of all, it's not limited to some specific lexicon. You use the words of the sentence themselves to annotate the sentence, so you're not bound by them. And the argument tends to be reduced. So that's another work that we had in ACL, specifically testing whether we get reduced argument spans from QA-SRL. And it turns out that the question-answer format, so if you have what did someone give, people would answer the necklace instead of the necklace which your mother gave her, and this can get very long. And they just break it when where you should break it, where you should break the argument. So overall, it seems that QA-SRL satisfies these requirements that we want from the OpenIE representation. So we converted QA-SRL to OpenIE, and I think I don't have time to go into all the intricacies of how we did that. But in general, when we look at the set of question-answer pairs for a specific predicate, we can convert that to OpenIE tuples. So in this case, we have three OpenIE tuples, so 3 question-answer pairs converted into 2 propositions in OpenIE. So from this question, we can take some stuff from the question and plant it in the right place. And there's special handling for nested predicates, for models, for propositions. So we can build this OpenIE structure from both information in the questions and the answers. So we did just that. We converted the entire QA-SRL representation in an automatic manner to OpenIE. And starting from 3,000 sentences, we got to around 10,300 extractions of OpenIE. And we validated this against an expert annotation just to have some sense whether we actually got to good extractions. And overall, this is 13 times bigger than the largest previous OpenIE corpus that we can that we have found, specifically the river corpus. So this is significantly bigger than previous OpenIE corpus that were created specifically for some task. And also, I think another nice property is that we didn't create this with a specific OpenIE parser in mind. So we didn't think, now we created an OpenIE parser, let's create an accompanying OpenIE corpus to test it. This is separate from a specific corpus.
So QA-SRL then is those annotations were designed to be complete then? Like everything that you could get, because you're trying to get something that you can measure recall against. So everything that you can get out of a sentence is gotten from the sentence?
For verbal predicates, yes. So this is definitely verbal OpenIE complete.
And how is that? Okay, I can see, but yeah.
So it's true that for non-verbal predicates, you wouldn't get annotations. But that's an interesting avenue for future work.
Just when you say 13 times bigger, you mean labeled corpus, right? The actual OpenIE corpus of the billions.
Yeah.
Just small.
Certainly. So this work was presented previously, and now we're working on a supervised model based on those annotations. So we start with the BIO encoding, and we have some variations compared to other encodings of BIO specific for the OpenIE task. So if you look at the sentence, May, I hope it's still correct in this time of year, May, the British Prime Minister plans Brexit, on which the UK has voted for last June. We want to tag this with BIO tags given some OpenIE extractions. So we have these gold OpenIE extractions, and we add BIO tags. So BIO tags beginning inside and outside with respect to a specific predicate. So we also have multi-word predicates. That's one thing. And the other thing, since this single predicate produces 2 propositions, we can repeat the same label. So we can have A0 repeated, and that indicates that we encode 2 different extractions here. One other thing I think that's interesting, if you look at the same sentence, but this time we look at the predicate has voted for, there's some semantics going on where it's not always the linear position of the argument that indicates where it would be in the OpenIE tuple. So here we can see that Brexit, for example, started the sentence even though it ended up on the second argument slot. So there's some interesting correlation between the argument label and the argument role. So saying that something is A1 is more than just saying it appeared after the specific predicate in the sentence for OpenIE. So it's somewhat of a softer notion of role as opposed to the more rigid SRL roles.
Question? Yes. Does this tagging scheme allow for overlapping space? Okay.
And some of my systems might say plans as the predicate rather than plans for. So it sounds like your guidelines distinguish which one's best.
I would say that if you need, so I have 2 answers for that. So one is, I think that as many semantic tasks, you can have some ambiguity. And I think we addressed that in the evaluation. So we wanted to be fair. I'll get to the evaluation in a second. But since we train on this specific corpus and we fit it, so our supervised model is kind of unfairly looking at some supervised corpus that the other systems didn't use. So I hope to compensate and be fair on the evaluation. So the evaluation would be very soft on whether you choose just a single sentence here, just a single word here, or you choose the entire span. I want to capture that both are fine. Similarly to translation or summarization, we can have various right answers.
Were the P's given as input to this task, or is that also a tag that's predicted?
We'll see in a second. Just the head was given because you can identify it as a verb. But no, in general, you need to predict the entire BIO scheme. It's a good question. So to your question, if we look at this sentence, Obama and Clinton were born in America. This is a bi-LSTM end-to-end model, which I said we're going to see a little bit of. So as you said, we identify this in advance. We know that this is a predicate in the sentence. And now we're predicting given this specific predicate. Okay, but that's the input that we get. And the features for the word born are propagated to all of the other features, word features in the sentence. So when you tag the word Obama, you know that you do so for the specific instance of born, as opposed to if you had some other predicates in the sentence, it would get a different tag. If we look at here, so the word PM is an A0 of plan, but it's O for voted. Okay. Yeah. So hopefully we get these tags. These are the correct tags for this sentence. So we introduce part of speech and pre-trained word embeddings to compensate for the relatively small amount of training data that we have. This was useful. And in addition, as I said, we concatenate the predicate head to all of the other words, and we expect to get these features from above. And I didn't mention this, but most OpenIE systems also have some confidence associated with each extraction. So we also want to have some confidence for this specific extraction. And we took a very simple approach of, so this is a softmax, so we have a distribution over the different labels. We took the most probable one and took a multiplication of the different probabilities for this specific tag as the confidence for the entire extraction. And I think that interesting follow-up work would be to have some more interesting confidence metrics here. Question?
You have two extractions from one sentence. How do you handle that?
So this is what happens here, actually. So this is the confidence of these tags. So they would both get the same confidence. You've got Clinton was born in America and Obama was born in America, and they're both predicted here.
Nice.
Yeah, I agree that I think future work can find better ways to model this confidence.
I've seen a number of different ways to include this, like, I'm looking for a specific predicate here. Did you try any other ways? Like, so you took the embedding for born and you concatenated it to everything? Other people have like tried as a 0-1 kind of binary.
Yeah, I think that's for SRL, right? For SRL.
And
encoding.
some other stuff?
Yeah, so I think we looked at, so definitely this is very, I mean, when you say other stuff, I think the most related task here is SRL, I think.
There's
yeah.
a similar thing for like summarization
that you need the predicate?
A few other times, it's not a predicate, but,
yeah.
but like, I'm looking for a particular thing and I can encode it with a binary flag.
Yeah. So I've seen that being done specifically in SRL, and we tried that specific option. We did try, and it didn't work as well as this.
That's interesting.
Yeah. But yeah, I think this is a work in progress. So I'm looking for ways to encode this better. So the evaluation. We tested against many systems, and here, just for simplicity, I just shown the best performing ones. Props is our system. I don't think we need to go too much into that, but we can if you want to. OpenIE 4 is by Mouthsum et al. And I think now there's OpenIE 5, I've heard yesterday. And Closey is also another good OpenIE system from recent years. So we had a very soft matching approach. Matching, if you match the head of a specific argument, it's counted as correct. That way we can overcome certain mismatches between spans. And here it's kind of hard to see that we do better. So RNN OAE is ours. But if you look at the area under the curve, you can see that we do 4% better than OpenIE 4, which does 4% better than previous state of the art. So all in all, it seems like we have like some advantage in some step over previous work. And again, this is soft matching. And if we would have counted exact matching, then it would be unfair for the other system as they would have done poorly. Yeah, so that's I said. And overall, I think it's interesting that most of the system don't get around 2% of recall here. And this is based on confidence, right? So this is precision recall based on the confidence. And I think that this is due to missed long-range dependencies and pronoun resolution that you need to do in order to achieve some of the extractions. And we can talk more about this if you're interested. Yeah.
So I don't think OpenIE 4 or these other things take the predicate as input. So are you like doing a pipeline for your RNN where you first predict the predicate and then?
So just pause tagging for taking the. I also don't get the predicate as input. I do it automatically.
So both,
just
so
outside. Yeah.
Outside
Outside of. I mean, pause tagging is pretty. Yeah. So I started pause tagging, which I didn't mention, and then I feed my. Yeah. So let's look at some analysis of this data. We looked at the number of extractions that we get. And the arguments per proposition, and this is, I think, this is a mistake. This should be characters per argument to see whether we get the correct number of propositions, all in all, from the text, as compared to the gold, which is the first one. If we get the right number of extractions, so the right number of predicates, to your question, the right number of arguments per predicate, and the right number of characters per argument. So overall, we see that our system tends to a little bit overproduce arguments and over-shorten them. So you have slightly shorter than we want arguments. And we also split the task for analysis purposes to differentiate between predicate identification. So to your question, if we need to identify also the predicate span, we wanted to see how well we do on just identifying the predicate span, and separately, how well do we do on identifying the arguments. So this is for identifying the correct predicate span, ignoring the arguments at all. And here I think we can see pretty clearly that actually RNN OAE is better at identifying the predicates in the sentence much more than the other systems, of just identifying the correct span of the arguments. And the argument identification is where the noisy parts begin, even though, again, if we look on the area under the curve, we still do better. And on these sections of the precision recall curve, we also do better. So I think this kind of, this is where we need to improve as opposed to predicate identification. Another analysis that we did, we wanted to see whether our system, since it's supervised, whether it just memorizes certain patterns for predicates it sees in the training set. Right, so we split the test set to seen and unseen predicates in the training set, and we recorded the overall performance of our system for these two sets of predicates. So we can see that for seen, this is the predicates that we've seen in the training set. We do better than we do for unseen, but overall we do get to generalize pretty well to predicates that we haven't seen in the training set. I think that's something nice to get. And overall, this is not a small portion. 24% of the predicates were unseen during the test time. So there is some generalization here. I mean, we don't see too much of a significant drop. Yes?
This is F1 on the whole triple?
The whole triple. So this correlates with, so this breaks down the first one that we've seen, which was kind of in the middle, right? Because we had a combination of both. Right, so to conclude, so this concludes my talk in general. So we get nice, yeah.
I was dying to ask a question, but I didn't
Sure.
want to interrupt you. But since
You can always interrupt.
So what do you think would happen to the RNN OIE if you had substantially more training examples? One would think it would substantially improve performance. So the reason I'm asking is that the way we used to label examples, your critique of the methodology was exactly right, but the way we particularly like labeling examples is using redundancy, right? So it seems like So the hypothesis was that if you have two distinct sentences that result in the same extraction, the likelihood is exponentially higher that they're the same, and of course even more so if there's three, and of course you can roll that into the confidence function. So effectively,
But that's for gold annotation?
well, these aren't gold, let's call them silver, but the point is, right, especially in the crowdsourcing era, that was one way to get a large number of somewhat noisy annotations. But again, given that you're using learning mechanism, silver quote-unquote annotations are great to feed in. So basically my question is, could you take 1 billion sentences, these are the modern days, I give you 10 billion, run whatever you want on them, get the small subset that's very high confident, highly redundant. You could validate to the site to make sure this is, but feed that into our NOA and see what happens.
Yeah, that's a great idea. And then we can test it on gold. I mean,
You can evaluate it on gold
yeah.
still, but
So
not-
my disadvantage of that would be that the model would fit that specific original system that produced those OpenAI tuples. But given that you can test on a separate test set, yeah, that's a good idea.
Right, and the other thing is, whatever it was, whatever the system was doing, right, the redundancy
Yeah.
gives you something.
I agree.
Right,
But and you can test that that's the case.
You can test those hypotheses.
Now that you have this corpus, you can test those hypotheses and be more certain that you're not overfitting the original
Yeah.
system.
It actually should be pretty easy to do.
Yeah, that's a cool idea. So to conclude, we've seen non-restrictive modification, some crowdsourcing technique, modeling with CRF, and I'm interested in following this up with distributive coordination. I think that you can use similar techniques to annotate non-distributive coordination and try to predict, to do similar work there. For supervised open information instruction, so as we've seen, better confidence estimation, model improvements, and using what Oren said could also be a good improvement. There's a lot of avenues that I think can be explored here. In terms of future work, like more general picture, what I'm interested in. So I think that having some layers of structured representation, so having the propositions extracted, and then adding some layers on top of that. I didn't mention that so Luke mentioned that I did a work on factuality, but finding some ways to add more annotations to an existing proposition framework, I think that's interesting. Crowdsourcing, as I've seen, and to learn from partial annotation. So right now we're working on a project where you don't want to get the full sentence annotated. You want to get some specific annotations from crowdsource and then learn from that the entire structure some way. And that way you can spend your money better, get more annotations that are not full, but for more larger amounts of sentences. Multi-sentence, that's something that I guess Ido talked about here yesterday, and that definitely interests me, how we can take proposition extraction to the multi-sentence level. And that would require coreference, which I think is a very interesting work to try and do, which incorporates a lot of semantic aspects that you need to solve in order to solve coreference. And finally, multilingual, that's also one possible future aspect. If you look at QA-SRL, for example, it's not clear that it's specifically bound to English, and thinking about, I speak Hebrew specifically, so thinking about it in Hebrew, I think it seems like it would work, and it seems interesting to try and maybe get an OpenAI corpus for Hebrew pretty easily with this methodology or similar or other languages. So thank you very much for listening, and I'd be happy to take your questions.